All right, let's finish chapter 5 and then we'll be halfway done. All right, there is about 75% probability that a truck will be going over the speed limit on I-80 between Cheyenne and Rock Springs, Wyoming. Suppose that a random sample of 5 trucks on this stretch of I-80 is observed. Okay, so we've got 5 trucks, so we know N is 5. And we know that the probability that they're speeding is 75%, so 0.75. Part A says make a histogram showing the probability that R equals 0, 1, 2, 3, 4, and 5 trucks are speeding. So what we're going to do, this is a binomial distribution again. Either they're speeding or they're not speeding. So we want to go to where N equals 5 on our binomial table. So N equals 5. And 75% speeding. So I'm going to come down here underneath 0.75. And we're going to write down these probabilities. The probability 0 trucks are speeding is 0.001. The probability 1 truck is speeding is 0.015. 2 trucks 0.088. 3 trucks 0.264. 4 trucks 0.396. And 5 trucks is 0.237. Okay, so that's where I got these probabilities that I wrote down. Now we can make our histogram. I just wrote I-80 as my title. This is the probability of our R values. On the side, our highest probability was 0.396, so I knew I need to at least get up to about 0.4. Okay, and then along the bottom, we have the number of trucks that are speeding. You know, the probability for 0 trucks speeding was really, really small. Okay, kind of the same for 1 truck, and then we kind of did this. And you can tell this is definitely skewed to the left, okay? But if we make it just like we did back in section 5.1, except for these probabilities we have to get out of the binomial table. All right, finding the mean mu of the probability distribution. Well, this is a binomial distribution, so we can use this easy formula, okay? Not the tough formula that we learned in 5.1 that works for any probability distribution. This is a binomial distribution. We can just take N times P. So we have 5 trucks, N is 5. The probability that it's speeding is 0.75. So 5 times 0.75 is 3.75. So out of 5 trucks, we would expect 3 or 4 of them to be speeding. Okay. Same thing on standard deviation. This is the binomial distribution, so we can use the easy formula. The square root of N times P times Q. Well, we have 5 trucks, so N is 5. The probability that it's speeding is 0.75. The probability that it's not speeding is 0.25. Multiply those together, take your square root, and you get 0.968. Certainly much easier than the formula that just works for any probability distribution. Okay. All right. A coach found that about 12% of all hockey games end in overtime. What is the expected number of games ending in overtime if 50 hockey games are played as a random sample? Well, again, expected number is just another way to say mean. Okay, so we're going to do this. This is a binomial distribution. Either they end in overtime or they don't. So we're going to use mu equals N times P. We've got 50 hockey games, so N is 50. 12% end in overtime, so 0.12. 50 times 0.12 is 6. So out of 50 hockey games, we could expect 6 of them to end in overtime. All right? Now to the more interesting problems. These are our quota problems. Records show that the probability of catching a northern pike over 40 inches at Talton Lake is about 15% for each full day a person spends fishing. So we know P is 0.15, 15% chance of catching a fish. But it doesn't tell us anything about our sample size. In fact, that's what quota problems are. We have to find the sample size. So part A says, what is the minimum number of days a person must fish to be at least 83.3% sure of catching one or more northern pike over 40 inches? All right, so my first thing I'm going to do is I'm going to write a probability statement. We want one or more. So we want the probability that R is greater than or equal to 1. Okay. Now, we want to be at least 83.3% sure. So writing 83.3% as a decimal is 0.833. So we want this to be at least, so greater than or equal to 0.833. So in other words, we want the probability of r equal to 1 plus the probability of r equal to 2 plus, and we don't know how far we have to go up, but we're going to do this until we get a probability that either equals 0.833 or goes above it. Okay? So what we're going to do is we're going to be looking underneath 0.15 in our table. Okay? So in our table, I'm going to go to 0.15. Now, we want to look at our values, 1, 1, 2, 1, 2, 3. So this first set, we have to look at the 1, 2. Okay? That does not add up to 0.833. Okay? Then I'm going to come down here to where n equals 3, and I want to look at the 1, 2, 3 and add those up. And again, that does not equal, or it's actually smaller. We want it to either equal or be greater, so not big enough. Then I'm going to go to n equals 4, and I'm going to add up the 1, 2, 3, 4. Again, that does not equal 0.833. Same thing at 5, 1, 2, 3, 4, 5. Okay? Does not add up to 0.833. At 6, 1, 2, 3, 4, 5, 6. Does not add up to be enough. At 7, 1, 2, 3, 4, 5, 6, 7. Still not big enough. Okay? Still looking under 0.15. At 8, when I go 1, 2, 3, 4, 5, 6, 7, 8, these numbers add up exactly to the 0.833. So we know n has to equal 8. So that's where I get this n equals 8. And a person must fish 8 days to be at least 83.3% sure of catching one or more northern pike over 40 inches. All right. What is the minimum number of days a person must fish to be at least 55.7% sure of catching 2 or more northern pike over 40 inches? All right, so now we want 2 or more. So I want the probability r is greater than or equal to 2. We want to be at least 55.7% sure. So that's greater than or equal to 0.557. So that means we're going to start with r equal 2 values. We're going to add up 2, 2, 3, 2, 3, 4, until we can get up to at least 0.557. So again, we're going to start at the beginning of our table. We're still looking under 0.15. And this time I'm just going to, under n equals 2, I'm just going to look at the r equal 2 value, and that's too small. Under n equals 3, I'm going to look at the 2, 3 value. Okay, too small. We need to add up to 0.557. Okay, when I look at the 2, 3, 4 under n equals 4, it's not enough. At n equals 5, I look at 2, 3, 4, 5. It's not big enough. Under n equals 6, I look at the 2, 3, 4, 5, 6. Not big enough. Under n equals 7, 2, 3, 4, 5, 6, 7. Still not big enough. At 8, I look at 2, 3, 4, 5, 6, 7, 8. Not big enough. Under 9, 2, 3, 4, 5, 6, 7, 8, 9. They don't add up big enough yet. Under 10, 2, 3, 4, 5, 6, 7, 8, 9, 10. Still not big enough. Under 11, I go 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Not big enough. At 12, when I add up 2 all the way down to 12, we get 0.556. But we need 0.557 or bigger. Okay? When we go down to this next one, it's going to be too big, which is fine. But this skips from 12 to 15. It was probably n equals to 13 that would work. I mean, we are so close here. However, the best we can do with our table is say, well, n's 15. Okay, so that's what I said, n is 15. And a person must fish 15 days to be at least 55.7% sure of catching 2 or more northern pike over 40 inches. All right, I'm over 9 minutes, so I've got to stop right here. There'll be a part 2 that's got part C on here.